now. Okay, so I'm going to be recording this part of the session. If anybody has any objections with the recording, please say so now. Okay, thank you. Okay, so we're gonna be talking about electrostatics, which is charges, electrical charges, and we've already talked a little bit about what electrical charges are, but we're going to go deeper into that maybe later today or surely on Monday. And they're going to be forces interacting. And so one thing I need you guys again to dominate is and remember is how to do free body diagrams and represent these forces that are going to be interacting in a body. So we're going to be doing some problems. I'm going to be doing 3 problems right now, and you guys are going to do some problems also that you're gonna have to turn in. If at any point anybody has a question, stop me and I'll stop me and we'll go through it. So we're going to be doing 2 sets of problems. Okay, these are relatively simple problems, I would say. But again, I need us to refresh these. The first part is just to draw and identify free body diagrams. Okay, I'm going to be doing for this set, I'm going to be doing problems 2 and 4, and you guys have to do problems 1, 3, and 5. I'll let you know how you're going to do these in a moment. And I'm going to be doing them here, and we're going to go through them. Okay, so you guys have this information here. I'm gonna jump over to the whiteboard here. By the way, a question, because I don't know this in Zoom. Just answer anybody. You're seeing the whiteboard right now, right?
Yes.
Yes.
Okay. Do you see the PowerPoint in the background?
No.
No.
Oh, okay. I just wanted to check how the windows were from what I was seeing. Okay, good. But remember, you guys have the PowerPoint there because I'm going to be referencing the problems. Okay. I found these problems on the internet and I found them amusing because there are different situations, and some of these situations have to do with animals, which I found a bit interesting. So I'm going to be doing problem number 2. What does problem number 2 state? Problem number 2 states, oh, by the way, for all these problems, what we want to do is to represent the free body diagram, where we look at the forces that are interacting. Okay. So problem number 2, it says a monkey pulling itself with both arms onto a tree branch. We want to represent that. By the way, I'm going to be doing 2 and 4. Try to do these in your notes while I'm doing them. And again, if you guys have any questions, let me know. So a monkey pulling itself with both arms onto a tree branch. How would we represent that free body diagram? Well, okay. I'm going to be doing some very ugly drawings, by the way, because drawing is not my forte. But maybe the ugliness of the drawings are going to help you guys remember some stuff. So problem number 2, a monkey pulling itself with both arms onto a branch. So what is the situation? This is supposed to be a tree branch. Okay. And we have a monkey. We've got a monkey. What color should the monkey be? Let's draw a monkey brown as well. We've got a monkey. I'm not sure how to draw a monkey. This is a monkey. It's a horrible monkey. It looks more like a cow, doesn't it? Looks like a cow.
More or less.
Thank you, Andrea. It was a rhetorical question, but yes, it looks like a cow. It kind of looks like a cow. My drawing is ugly, but again, you guys should get the gist. And he's got his monkey legs here hanging. And so here is the monkey hanging from the tree. That's the situation. He's backwards, by the way. Here's his tail. So here's the monkey hanging from the tree, and the monkey is pulling itself upwards. Okay. We want to represent this situation in a free body diagram and look at the forces that are interacting. Okay. So the free body diagram is going to be represented as a reference with a reference frame. By the way, a free body diagram can be represented in 2 dimensions or in 3 dimensions. Well, actually, a free body diagram can be represented in 1 dimension, 2 dimension, or 3 dimensions. Okay. Normally, the ones we're going to be talking about at the beginning are going to be 2 dimensional. There are going to be some 3-dimensional situations. So we're going to have an X and a Y. And what we're going to represent in these coordinates are going to be the forces. Can somebody tell me at least one of the forces that is being that's happening that's happening here in this situation? Let's see. Let me.
Gravity.
Gravity.
Yes.
Gravity. So we've got gravity. We always know that gravity is going to be going down. So we've got gravity. Ricardo, go ahead, please.
We have the force of the branch supporting the monkey.
There, the monkey is being held with 2 arms and it's pulling itself up. So there is an interaction, and remember Newton's laws, there's an interaction between the branch and the body of the monkey being pulled forward, and there are forces interacting there as well. So we're going to have forces here that have to do with the arms of the monkey interacting with the branch. Okay, let me see here, because remember to lower your hands if you're not going to participate or you've already participated. So I know. So let's see, Juan Ignacio, go ahead.
Is it the weight of a monkey?
Yes. So Giselle said that one thing that was happening here is that we had gravity. Now the monkey has a certain weight. Now remember concepts here that are very important. The monkey has a mass. Okay, a mass is a property that the things have, and the mass multiplied by gravity is the weight. So the monkey has a certain weight, and that weight is going to be one of the forces that are affected. Enya, please go ahead.
Professor, in this type of problem, do we have a normal force?
Oh, that's a good question, Enya. In this type of problem, for this particular situation, no. And that was a question I'm going to ask you, because we're going to be seeing 2 situations. Right now, in this situation, there isn't an opposition that's making the monkey stay where it is. Because notice that the problem says that the monkey is being pulled forward, pulled upward. He's pulling himself upward, okay? So there isn't a surface that's creating contact, because the normal force is when we have an object and there's a surface that's creating contact that reacts to the weight, okay? So in this case, one of the forces that we're going to have, I'm going to draw these here. I'm going to put this in. We're going to have the weight of the monkey that's going to be going down, because gravity pulls us down. And this is going to, I'm going to call this W, okay? And then we've got the forces of the arms of the monkey that are pulling itself upward. Oh, by the way, I didn't mention something, I'm sorry. When we do a free body diagram, we're locating the free body diagram in a certain place, and that's our reference. So right now, the reference for the free body diagram is the monkey. It's not the branch. It's the monkey. Okay. And so we're also going to have 2 forces that are going to be having to do with, I'm going to call this F right, F left. We're going to have 2 forces here that are going to have to do with the reaction or the pulling towards the branch. This is going to be FR, and this is going to be FL. In the end, those forces are going to be related to each other, and in the end, we can see how to combine them, or how they're going to be distributed. But this would be the free body diagram for situation number 2. The monkey pulling itself up the branch. Okay. Right now, the only interactions are vertical. So we only have forces in the y-axis. There isn't a situation we could be saying, well, besides that, there's a wind that's gushing and it's making the monkey sway towards the left. Well, that would be something we would represent in the x-axis. But right now, we only have those two. We only have forces along the y-axis. Okay. Again, right now, the only thing we're doing, we're not solving the problem because we don't have any data that are being given about these forces. We're just trying to represent the situation. Is this clear to everybody? Questions?
Professor, what did you say about gravity, please?
Okay, gravity is important. Whenever we have an object and whenever, this is an important question that I'm going to relate to what we're going to be seeing in the class. Before in statics and dynamics, Lisa, we were talking about objects on Earth or somewhere where there is an interaction between these objects and a force of gravity. So whenever you have two objects, and in this case, the Earth is a very large object compared to us, there's always going to be an attraction force that is going to be gravity. Okay, so if you have an object here on Earth, for example, the monkey has a mass. Okay, the mass are the kilograms. So let's say that this monkey is a 2-kilogram monkey. Okay, the force that's going to be exerted towards the Earth is going to be represented by the mass multiplied by gravity. And that's the weight. That's the force in newtons. Okay. And so the mass multiplied by the gravity, that's always going to be the force that pulls us towards the Earth. Okay. Are we okay up to this point, Lisa?
Yes, I didn't saw the, no, I got confused myself. I already understood. Thank you.
But your question is importantly said, and remember, everybody, when you ask a question, turn on your camera so you pop up in my screen. But it's an important question because of the following: the monkey, even if the monkey is very small, would you agree that the monkey has a weight, and we need to consider that weight, right? Thing is, in the types of situations that we're going to be talking about here in the course in electricity and magnetism, things are so small that we don't care about the weight. So we might be talking about an electron and the forces that an electron exerts on another charged particle. And in that situation, we could incorporate the weight into the problem, but the weight is going to be so small because these particles are going to be so small that the weight is going to be negligible. Because, by the way, protons, electrons, they have mass. They have a mass, and they have a weight. But it's so negligible in comparison to the electrical forces that we don't have to consider them. Okay. Now, before we go to the next situation, because we're going to compare them, any other questions with this one? Okay. Okay. Alejandra, are you there?
Yeah.
Okay, Alejandra. Okay, wrong answers only. Do you like my drawings? Are they good?
Yeah.
That was the wrong answer. Wrong answers only. So that was a good answer. My drawings are terrible, but are they understandable at least?
Yes, they're better than what I would do.
Well, that's I try. My daughter's good at drawing. I didn't inherit any of that, but at least as long as you guys can understand them, that's good. So good. Wrong answers only. Thank you, Alejandra. Now let's go to situation number 4. I'm sorry. And I'm gonna. I don't want to. Okay, I don't want to close this, so I hope it doesn't get closed. Okay, so now let's look at situation number 4. A fallen tree is resting on 2 sides of a river, creating a bridge. And we want to see the free body diagram of that one. Okay, a fallen tree is resting on two sides of a river, creating a bridge. Okay. Let's look at that situation. Oh, what happened? What I thought happened, oh no, I thought this was going to be erased. Thank God it wasn't. Okay, so now let's look at problem number 4. So we have a so these are green pastures. And we have a river that's flowing through here. And we've got a tree that has fallen across this river. Trees have branches. That's how we know they're trees. So the tree is falling here. And it is creating a bridge. And we want to represent the free body diagram of this. Now, notice that what I'm doing here is I'm looking at the skywards view of it. Okay. And if I do the free body diagram with the skywards view, I'm not necessarily going to represent the forces that I need to represent or understand. So actually, the way I'm going to be looking at this is that I'm going to be looking at the situation. So my eye is going to be here. So I'm going to be looking at the tree this way. Okay, I'm going to be looking at it at a sideways view to do the free body diagram. And let's look at the free body diagram, or how the free body diagram for this situation would look like. Can somebody tell me what forces are interacting here?
The weight again.
Exactly, the weight again. Good, good. Andrea, I believe it was. So the tree has a mass. The tree has a mass. And that the tree has a mass, and because the tree has a mass, there is going to be a weight that's being exerted downwards. Okay. What other forces are involved? And I'm going to go back to, I believe it was Enya that asked a question in the previous one that had to do about something here. What other forces are going to be involved here?
The
normal
side?
force.
Normal. So the tree is resting on the two sides of the riverbed. And so we're going to have the force here. That's going to be the weight. And then there is going to be a reaction force here. There's going to be a reaction force here and here, where the place where the tree is resting, there's going to be a reaction force that's usually this normal force that we have. So I'm going to call this F normal 1, and I'm right. I'm going to call this one F normal left. And we're going to have these two reacting here. Okay. And that's going to be the situation that we're going to have there. The weight and the reaction, normal forces. So anything that's resting on anything else, okay, anything that's resting on anything else, if I put my cell phone here, try to balance it out. There's a weight of the cell phone going down, and there's a normal force because of the contact of the surface of the cell phone that's reacting to the weight that's going up. Is it clear that this would be the free body diagram for situation 4? Questions before I ask you guys some questions.
No.
Now, let's see. The two diagrams look the same. So it would seem that the situations are the same, right? But they're not. Can somebody tell me what's the difference between this situation, the situation number 2 and situation number 4? The two free body diagrams look the same. Andrea, I think, let me see who raised their hands. Let's see, Andrea, go ahead.
Is
And remember
that,
to turn on your cameras, please.
I don't know if the one of the tree is like left on the floor and he's having contact with the surface.
The surface,
And the other one doesn't. It's like hanging.
It has to do with that. So in the tree is resting on the surface. That's the key. It's resting on the surface. In the situation of the monkey, you said something. The monkey is hanging. Actually, the definition of the problem doesn't say that. The definition of the problem says that the monkey is pulling itself upwards. So there's a difference there. It isn't the same that the monkey is hanging as if the monkey is pulling itself upwards. So it does have to do with what you're mentioning, Andrea. Ricardo.
Can it be explained that the monkey problem is like dynamic and the tree one is static?
There you go. There it is. Well done, Ricardo. I'm going to start with the second one. It's exactly that, Ricardo. The two free body diagrams and representations of the forces look the same. However, for problem number 4, I'm sorry, this situation is the system is static because the tree is resting and nothing's moving. Over here, the definition of the problem says that the monkey is trying to pull itself upwards. That means that there is movement. So this is dynamic. Good job, Ricardo. That's the main difference. Now let's go a little bit deeper onto this. Now, again, one is static, one is dynamic. In the static, nothing is moving. In the dynamic, we have movement. The two free body diagrams look the same. What's going to be the difference then between the two situations? Now, mathematically. Viviana, please go ahead.
Is it that the monkey is exerting force and the tree is resting?
It is that, Viviana, but I'm going to stay with you. Now let's go mathematically to that. If something in the situation of the tree, like you mentioned, everything isn't moving, it's static, right? And in the case of the monkey is moving, it's exerting a force. So mathematically, in the second situation of the tree, Viviana, what is the total force of that system?
0?
It's 0. Yep. So I'm going to write that down here. If I do a sum, there are no forces in X. So if I do a sum of forces in X, well, it's 0 because there are no forces in X. Would you agree, Viviana?
Yes.
And in this situation, if I do a sum, that was an ugly, if I do a sum of forces in Y, I'm going to have the normal forces, F and L, and F and R that are going up, minus the weight, but this is also going to be 0. They have to cancel each other out because the tree is resting. Okay. Now, I'm going to stay with you, Viviana, because you raised your hand. Sorry about that. I'm not picking on you. What would be the difference then in the dynamic situation, Vivian, if I were to write down the equations?
Can you repeat the question? I'm sorry.
In the dynamic situation up here, what would be the difference? So let me help you out. The sum of forces in X, what is that going to be equal? It's 0 because we don't have any forces in X. But what's going to happen with the sum of the forces in Y for this situation? I've got FR plus FL minus the weight. What is this going to be equal to?
Well, we don't know because we don't have data, but it's not going to be 0.
That's the answer, Viviana. It's going to be equal to something because there's movement. It's not going to be equal to 0. Actually, it's going to be equal to a net force, which is the resultant force. If the monkey is being pulled upwards, that means that the force that it's exerting with its arms is going to be greater than its weight. So that's why it's moving forward. That's going to be a net force that's obviously going to be positive. The net force in this situation is going to be going upwards. And in the end, that net force, according to Newton's laws, has to be equal to the mass, in this case of the monkey, times an acceleration. That, as you mentioned, Viviana, we don't have the numbers to do the calculation, but it's going to be equal to that. Okay, is that clear? Good. Okay, I'm going to leave you off the hook, Viviana, don't worry.
Yes, it's clear. Thank you.
Thank you, Viviana. So for the rest of you, was this explanation and differentiation clear? Questions? Okay. I'm gonna save a screenshot of this because I'm actually proud of my drawings. This was not as bad as I thought it would be. Let me just move my window and take a screenshot of this so I can add it to the. Oh, by the way, remember you guys that the PowerPoint presentations? Remember how I work in my PowerPoint presentation? So this PowerPoint presentation of Learning Module 1, I don't remember the version, but I think it's version 3. You notice because the file says V3. Every time we do a problem like this one, this solution is going to be included into the PowerPoint after I finish, and the file is going to be updated. Okay, so always remember to have the latest version of the file. This file of Learning Module 1 is going to be growing. I think it's going to be we're going to probably end up with version 12 or 13 or whatever. But all of this is going to be there. Okay, let me take a quick screenshot. Okay. Sorry about that. Okay, questions with questions with these two problems. Anybody? Are we good? Remember that when I ask a question, just so I know I'm not, yeah, just at least react, okay? So are we good right now with these two? Any questions? Okay, good. I just took a screen save, so I'm going to clear the drawings. And now we are going to, okay, now let's start adding some numbers here. Now let's do part 2, because right now when we were talking, Viviana said, you know what, well, we don't know the value because we don't have values. Well, let's add some values and now let's do some calculations, okay? Now for these situations, what we want to do is not only create the free body diagram, but also do some calculations to find the net forces that are resulting from the interactions, okay? I'm going to do problem number 1, and we're going to look at problem number 4, and you're going to do the other ones, okay? Okay. Okay, so let's look at these situations. I'm going to look at situation number 1. It says you push a 10 kilogram table across the floor with a 20 Newton force. The friction is 4 newtons. Oh, by the way, I'm going through, I'm not going into detail about some things that should be obvious that have to do with units. So kilograms are units of mass. Okay, we're talking about mass with the kilograms. This is mass. All objects have mass, so this is mass. And the newtons are a representation of force. Okay. One thing that I love about electricity and magnetism, that's really wonderful, and I don't know if you guys have ever thought about this previously when you've taken these topics, but what's the main, can somebody tell me what's the main problem with units that we have? So right now, everything that's there, it's in kilograms, right? But what's the main problem that we have in units? If we're talking about kilograms, meters, etc. Anybody?
There are a lot of different units in different systems.
The systems. I think it was Jose Luis. The systems. So we've got the international system. Well, I'm sorry, we've got the metric system, and then we've got the non-metric system. And so we've got meters. So right now it's kilograms, but it could have been pounds. And there's even a confusion there because pounds can be used as mass or as weight. So it's so yeah, it's are we going to travel 1 kilometer, or are we going to travel 2,000 yards, or are we going to use miles, or are we going to use feet or centimeters? So what Jose Luis mentions, there's this thing with units and systems. One thing I love about electricity and magnetism, it joins people and gets rid of all that. So in electricity and magnetism topics, if we're going to be talking about electrical charge, it's going to be coulombs. Wait a minute, is it coulombs in the international system or the metric system? It's going to be coulombs. I don't care what country you're from. It's going to be coulombs. If we're going to be talking about any other unit, if we're going to be talking about current, it's going to be amperes, amps. Here in China, in the United States, it's going to be amps. Voltage is going to be voltage units anywhere. So that's kind of cool about electricity and magnetism, that it's kind of a place where we don't care where we're from, and the units are all going to be the same for everybody, which is actually kind of cool. That doesn't happen with other situations that we were talking about. So let's look at problem number 1. I push a 10 kilogram table across the floor with a 20 Newton force, and there's friction. Now, how do we interpret friction? Friction is going to be a reactionary force, a force that reacts to movement. And usually friction, we're going to have that in surfaces. And it's going to depend on the type of surfaces where there's going to be this reaction to a movement. So I'm going to jump over here to the whiteboard. And this is problem number 1 from the second section. And so for this problem, see if I can draw this, there's going to be a table. Table is in a surface. And I am going to be here. Pushing. Does it say pushing or pulling? Pushing. Yep, I'm going to be pushing the table. That's me. Happy as heck. Okay. I'm going to be pushing the table. And so we want to see the forces that are interacting here. So somebody tell me what forces are interacting there.
The mass, the weight of the table.
The weight is going to be something that's going to be there. Good.
The force to the right too.
Yep, it's being, so I'm pushing. So that means there's going to be a force on the right. So there's going to be, first off, there's going to be a mass, and that means that there's going to be a weight. It's going to be mass times gravity, and there's going to be also a force going this way.
And the opposite friction.
Yes, so there's going to be this force here. Then I'm going to call this FP. And I think, Giselle, I think you raised your hand.
Oh, yes, but I was going to say friction too.
Oh, okay, good. So this FP are pushing, and then there's going to be a reaction force over here. I'm going to put it here on the bottom. There's going to be a reaction force here that's going to be the friction. I'm going to call this FR. And yeah, go ahead.
And the normal force.
Yeah, exactly. Very good. There's going to be a normal force. The normal force actually has to do, and is gonna have to do with the friction. So since there's a weight coming downwards, there's going to be a normal force that's going to be the reaction force, and depending on the weight, the friction coefficient and the normal is how we're going to how the friction react. And so let's do the free body diagram. We've got X. We've got Y. And we're going to write down the forces here. So we've got a normal force going up here. We've got the weight down here. And we've got FP, which is the pushing force going this way. And we've got FR in this way. Now we know some of these values. So we know that the weight is going to be the mass times gravity. Estrella, go ahead, please.
Professor, why FR? What does it mean, FR? The force R.
The force R, this is the friction force.
Oh, okay.
I just put FR just because for friction, but you can actually, the naming, don't really pay much attention that there's a nomenclature here. I'm just naming things to identify them. But
Yeah, I didn't know what friction, I mean, what, what's the name?
If it represented something, but it's the friction force.
Friction,
And so let's represent the data we have. So the weight is going to be mass times gravity. So it's 10 kilograms times 9.8 meters per second squared. This is going to be gravity in the metric system. So it's going to be 98 newtons. And we've got some other data here. So I'm pushing it with a 20 Newton force. So FP is going to be 20 newtons, and FR, which is the friction reaction, is going to be 4 newtons. Okay. Now there's movement here. So what we're going to do now is do the sum of forces in X is going to be equal to, we're going to take, the references can be really however we want, but we're going to take the Cartesian plane as it is. So right up is positive, down left is negative. So the sum of forces in X are going to be FP minus FR, which in this case is going to be 20 newtons minus 4 newtons. And this means that in X, we've got a total force of 16 newtons going this way because I'm moving it. Now, what would the sum of forces in Y be? Well, we're going to have the normal and we're going to have the weight. Okay. What would that be equal to? Okay, so we've got the forces, the sum of the forces in Y, and we've got the normal minus the weight. But what's that going to be equal to? Can anybody tell me? We know the weight. We know the weight.
We don't
don't-
know the normal.
We don't know the normal, but I'm going to ask the following question. Remember, because again, I need you guys to use your imaginations for the electricity and magnetism part. That's where we're talking. That's why I'm taking time with these problems. I'm pushing the table forward. So the table is moving to the right. Does everybody agree with that?
Yes.
Yes.
Is the table floating?
No.
No.
Is the table being lifted?
No.
No. So is there movement? Exactly, Diego, you wrote it in chat. Is there movement in Y?
No.
No. So the weight and the normal is going to be equal to the weight. They cancel each other out. And so, excuse me, somebody said something. I'm sorry.
Oh, if they're the same,
Yeah,
so they cancel.
they cancel each other out. Somebody's at the door, and that's why the dog is barking. Give me one moment here. Okay, so there's no movement in Y, so the normal and the weight cancel each other out. So the sum of the forces in Y is going to be equal to 0. So the net force that's being that's happening in this situation, I'm going to call this the net force, is always going to be equal to the resultant force of the forces in X squared and the forces in Y squared. Since the forces in Y are 0, then this is going to be equal to the sum of the forces in X. And so the only force I'm going to have is going to be the 16 newtons going this way, which is congruent with the problem. Okay. Now, this problem, we could add some variations to this problem where we could say, okay, I'm not only pushing it forward to the right, I'm also exerting to make it easier for me to move it. I'm also exerting a force here downwards to kind of lift up the table. Well, that situation would have been different because we would have had another force, and the sum of forces in Y wouldn't necessarily be 0 depending on how I apply that force. Okay, but for this situation, it is 0 because we have no we have no vertical movement. Okay. Okay, questions with this one before we move on to one that's a little bit more funky. Questions?
No.
No? Okay. Mhm. Okay. Now, let's look at another situation here. So we'll clear these drawings. Let's look at problem number 4. I don't know why this situation would occur. I kind of invented this problem based on the previous ones. I don't know why there's a bunny, a deer, and a monkey that are somehow, I don't know if this is a Disney thing or I don't know, but there's a bunny, a monkey, and a deer that want to trap a bear. The bunny, the deer, and the monkey are each positioned at the vertices of an isosceles triangle. The bunny and the deer are at the base of the vertices, and the monkey is at the pinnacle. The bunny and the deer are each located 1 meter from the bear and 1 meter from each other, while the monkey is 2 meters from the bear. The bear has been shot by a tranquilizing dart and is in the middle of the triangle tied to 3 ropes that are held together by the other 3 animals that are pulling them. The bunny is exerting a force of 1 Newton, the deer a force of 10 newtons, and the monkey a force of 3 newtons. They are located on shear ice, and so friction is negligible. We don't have to worry about friction. Okay. I am going to give you guys. I'm going to give you guys. Oh, I think I wasn't sharing it. So this is the. This is the problem. Problem number 4. That we were talking about. I am going to give you guys a few minutes to try to do at least the free body diagram of the problem. I'm going to give you a couple of minutes, 2-3 minutes to try to work on this problem individually. Okay, just grab a sheet of paper, at least to try to represent what we're talking about in the description of the problem. And after a few minutes, we're going to come back and we're going to solve it here. Okay, so I'm going to pause the recording for a moment here to let you guys think. Okay, we're back. Let's see how we can tackle this problem. And I'm gonna solve it here, and you can kind of compare with what you did. And if you guys have any questions, let me know. Why this situation would occur with a bunny, a deer, and a monkey trying to trap a bear, I have no idea on sheer ice. But well, there it is. Just out of curiosity, do any of you, or have any of you seen or identify a cartoon? I don't remember where they used to show this cartoon. I think it was in MTV or VH1. I don't remember that. It was called the Happy Tree Friends. Has anybody seen that cartoon? Just reactions. So, Ricardo, you have, some of you have. So imagine it's a Happy Tree Friends situation. That's the type of funny animals that we're dealing with. So yeah, it's kind of like a Happy Tree Friends situation here. So let's look at problem number 4. So something that's going to be very important for the work that we're going to be doing is that we need to visualize the situations. And that's why there's some information that's being presented, and we need to visualize the situations. Okay, so let's try to visualize this situation. So first off, we have a bear here. For some reason, the bear is here in the middle. He's been shot by a tranquilizer dart, and we've got a bear there. And then we've got 3 animals that are trying to pull, that are tied to the bear and trying to pull it. And so let's see the order here. We've got the bunny, a deer, and a monkey. The bunny and the deer are located at the base. So we've got a fluffy bunny here. It looks like a chicken. It should be more like this. We've got that's supposed to be a bunny. We've got a fluffy bunny here, and then we've got a deer over here. Let's put some antlers here. Looks more like a moose. Here. Looks more like a moose. And we've got the monkey, this monkey that's still with us for some reason. We got the monkey. It's a green monkey. We've got a green monkey up here. The monkey that kind of looks like a cow. We've got those 3 there. And they form an isosceles triangle. And so we've got a triangle that's being formed here between the 3 of them. And there's some information we're being given regarding this triangle. And so we've got some distances here. We know that the distance between the bunny and the deer is 1 meter. We know that the distance between the bunny and the bear and the deer and the bear is also 1 meter. And we know that the distance from the monkey to the bear is 2 meters. Okay, that's kind of the representation of the situation. And we've got some forces that are interacting here. And so I'm going to use purple. The monkey is the bunny is exerting a 1 Newton force. I'm going to call this F bunny. 1 Newton. The deer, which apparently is the strongest, is exerting a 10 Newton force. And the monkey is exerting 3 Newton force. We also have the weight of the bear, but there's something interesting here. Right now, we're looking at this in 2 dimensions, looking upwards. But actually, the weight of the bear, I'm going to call this W. The weight of the bear is a force that is going into the screen. Would you guys agree with that? You see that? Notice that I put an X there. Actually, when we're talking about 3-dimensional forces in electricity and magnetism, when we're looking at a flat surface, things that are going in are going to be represented with X's because it's like you're looking at the backwards part of an arrow. And there's another force, and I'm going to call this the Enya force because she's mentioned it in the beginning, which is the normal. And the normal force is going to be going upwards. It's going to be going towards me or towards yourselves, going out of the page. Notice that I'm representing that with a little dot. When we represent forces that are coming out of the page in 3-dimensional space, then it's represented with a dot. Now, let's questions up to this point with the terrible drawing of the animals and the situation. Questions with the situation. Is that clear? Ricardo, please go ahead.
So just one question. So we're looking at the triangle from like if we're underneath the ice and we're looking at them, or as like a bird's eye view?
Bird's eye view.
Okay.
We're looking at a bird's eye view. That's why the weight is going into the ice. It's going into the page. That's why it's a cross, and the normal is going outwards, and we represent that with a point. Okay. Okay. Now let's talk about the free body diagram and how that would look. I want to ask you guys a question because this problem has a lot of data and some of it we're not going to need, by the way. Do we really care about the weight and the normal for this situation?
No.
We don't, because the bear isn't being lifted up. And it says in the problem that it's shear ice, so there's no friction. So actually, we don't need to look at this in 3-dimensional space. What we're only interested in is the net force in the plane where we're looking at it. So we really don't need the weight for any part of this problem. We only need to know in this sort of pull that these 3 animals are doing, where is the bear moving towards? And we might have an idea of that because the deer is exerting the larger force. However, it's exerting it at an angle. So let's look at the free body diagram here, how the free body diagram in this plane would look like. This is going to be X and this is going to be Y. So we're going to have a 3 Newton force going directly upwards, which is going to be Fm of the monkey. We're going to have a force that's going to be going downwards here, which is the force of the deer. And by the way, this force is going to have an angle. I'm going to call that angle alpha. And then we're going to have the force of the bunny, which is FB. And that is also going to have an angle. Would all of you agree that that angle is the same one? Why? Because of the configuration of the triangle. It's basically, we are talking about this angle here. This is alpha, and this is alpha as well. We don't know that angle, by the way, right now. And so before we do any other calculations or stuff, what's going to be happening here is that this is a dynamic situation. So we're going to have the sum of forces in X is going to be FD, the force of the deer, times the cosine of alpha. Why the cosine? This is a very simple thing that you guys have to remember. When the angle is with regards to a certain to a certain line of the Cartesian plane, the resulting force in X in this case is going to be the cosine of that angle. The resulting force in Y is going to be the sine. So cosine is going to be related to the axis where we're measuring the angle from, and sine is going to be represented with regards to the opposing axis. So it's going to be the cosine of alpha minus FB times the cosine of alpha as well. And I'm going to leave that there for now. The sum of forces in Y, let's start a little bit lower. The sum of forces in Y is going to be equal to Fm, which is the force the monkey is exerting, minus, because they're going downwards, the force of the bunny times the sine. So first, the force of the deer times the sine of the angle, minus the force of the bunny times the sine of the angle. Okay. Questions up to this point? And we don't know the values of those. How do we find that angle? Well, we can kind of do a zoom of this triangle that's being formed here. And we know that this is 1 meter, this is 1 meter. And if I draw a line dividing the triangle in the middle, then this is going to be 0.5 meters, and this is going to be 0.5 meters. So if I'm looking for alpha, which would be this angle here, or rather, I'm looking for if I'm looking for alpha, the cosine of alpha is going to be 0.5 divided by 1, which is 0.5. That means that the angle alpha is going to be the inverse cosine of 0.5. Can somebody please help me out with that calculation? What's the value of alpha? The inverse cosine of 0.5. In degrees, please. Anybody?
60.
60 degrees. Thank you. 60 degrees.
I have a question, Professor.
Yes, go ahead, Lisa, please.
Let me turn my... the 2FB are for bunny.
Yes.
Oh, okay.
B is for bunny, D is for deer, and M is for monkey. Remember, my writing it's much better with the new stylus I got, but it's still sometimes kind of funky. So if any of you don't understand something I'm writing, please, please tell me, okay?
But Professor, why the bunny is on X and Y?
That's a good question, Lisa. Because the free body diagram, Lisa, is located here. Is located here in the bear. And so if I'm located here in the bear, Lisa, the bunny is pulling this way. You see that?
Yes.
And there's an angle. So since there's an angle, that means that that force that the bunny is exerting has a part of that force is going to be in X and part of that force is going to be in Y.
Okay. Yes.
And so we need those two components. It's not the same with the monkey. The monkey is directly aligned with how I place the Y-axis. So the only force that the monkey is exerting is along the Y-axis. But for the deer and the bunny, we do have components in X and Y. Okay, is that clear, Lisa? Okay. Now, and I'm gonna let you guys go in a minute. Don't worry. Let's go back over here. So now we're gonna have that the sum of forces in X is gonna be FD, which is 10 newtons times the cosine of 60 degrees. Newtons times the cosine of 60 degrees minus the bunny is 1 Newton times the cosine of 60 degrees. If you guys want to leave earlier, help me with the calculation. Somebody tell me somebody calculate this, please. And I'm going to go over here at the bottom. The sum of forces in Y is going to be equal to Fm, the force of the monkey, which is 3 newtons, minus the force of the deer, which is 10 newtons, multiplied by the sine of 60, minus the force of the bunny, which is 1 Newton, multiplied by the sine of 60. Please, you guys, help me out with these two values.
I got 4.5 on
For
the
that,
X.
for the X, 4.5. Please, everybody else verify. Okay, thank you.
Yes, I got that too.
Got the same.
Perfect. For the force in Y, please. Somebody calculate the force in
I
Y.
got minus 6.5, but I don't know if it's correct.
Yes, me too.
Minus, yep. That's
Minus
not,
6.5.
that's not incorrect. The signs are going to be important, Estrella. The signs are going to be important. So yes, minus, it makes sense. Minus 6. Why does it make sense that it's negative? Of the three
Because-
animals, who's pulling the strongest?
The deer.
The-
And where is the deer? It's in the bottom, according to my free body diagram. So it
Okay.
would make sense that there's more force towards the bottom than towards up. So that's why it's minus 6.5 negative. And I'm glad that that kind of doubt came about, because what does this mean? This means that the net force has a component that's going this way. That's the sum of forces in X. And it has another component that's going, whoops, it's going this way. That's the sum of forces in Y. So where is the bear moving towards? In what direction is the bear moving? The bear is moving in this direction. With a net force that we're going to calculate. What is this net force? This net force is going to be equal to the square root of the sum of forces in X elevated to the square plus the sum of forces in Y elevated to the square. Somebody give me this value, please.
7.9.
7.9. Thank you, Enyan. Please corroborate. 7.9 newtons. That's the force that's being exerted on the bear. Now, in what direction specifically? Well, there's another angle here. There's an angle here that I'm going to call theta. And so theta is going to be equal to the inverse tangent of the sum of forces in Y divided by the sum of forces in X. Please, somebody give me that value. inverse tangent. Oh, by the way, something very important, going back to Estrella's doubt about the sign. When we do the net force, the signs don't matter because they're elevated to the square. But when we calculate angles, we need to use we need to use the sign. It's important. Can somebody give me that value?
Minus 55.3.
So it's going to be minus 55.3. And why is it minus? Because the angle is coming from here to here. So that's the net force that's being applied on the bear. Okay. Questions with this? Was it clear to everybody what we did and how we got
Yes,
there?
sir. In
Yes.
the division, so I divide 6.5 divided by 4.5. I don't
Mhm.
consider the sign.
You should consider, you can consider the
Yeah.
sign. Yeah.
Okay.
And so these are kind of the types of problems we're going to be doing at the beginning. But instead of a monkey, a bunny, a deer, and a bear, we're going to have electrical charges. And the forces are going to be given by the signs of the electrical charges. So that's why I needed for us to review this. I'm going to take a screenshot here. Okay, questions with this one before we wrap up? Okay, I'm gonna switch over. I'm gonna stop.